we'll start doing complex numbers. And what are they? For example, if you have a function like x, we'll change the color. If you have a function like x squared plus 2x plus 10, 2x plus 10 equals 0, and you want to find the solution to this equation, you will have x1, 2, you know the formula is minus b plus minus square root of b squared minus 4ac divided by 2a, and that becomes 1, 2 is minus 2 plus minus square root of 4 minus 4ac, that's 40, and divided by 2. So that becomes minus 2 plus minus square root of minus 36 divided by 2. See, square root of 36 is 6, but the square root of minus 36 is impossible. So in order to make this possible, we say that we introduce something called square root of minus 1 is equal to I. So we say that, and then we make possible this solution here. So that becomes x1, 2 becomes minus 2 plus minus square root of minus 1 times square root of 36, you know that, and becomes divided by 2a. So it becomes minus 2 plus minus I. Square root of 36 is 6 divided by 2. That becomes, all can be divided by 2. So it is minus 1 plus minus 3i. 1 plus minus 3i. So you have two square roots. So we can then say that x is equal minus 1 plus 3i, and x2 is equal to minus 1 minus 3i. So these are the two square roots. So if you now multiply them back to see whether we're going to get the solution, that's correct. So let's try whether what we've done is correct. So let's check that. So what we're going to do, we're going to say x minus 1 plus 3i times x minus 1 minus 3i. What's that? So it's x plus 1 minus 3i multiplied by x plus 1 plus 3i, and that becomes, so if you make that separate like that, so that's a minus, so that here is a minus b times a plus b, which is a square minus b square. So that becomes x plus 1 square minus b squared, so it's 3i squared. So let's continue that further down. So x plus 1 squared, that's first and the square plus 2 times first times second plus second square. So I minus 1, so from here we have that I square equals minus 1. So that's another thing to remember. All these two you need to remember. They're important. So I square, so here we have that here minus I square is minus 1, so minus times minus is plus. 3 square is 9. So what that becomes, x squared plus 2x plus 10, which is identical to what we started from. So these are the complex numbers. That's how we introduce and work with complex numbers. Let's say how do we show them, how do we denote them. Say for example we usually use letter Z as to say that's a complex number, therefore it consists of the real part and imaginary part, as we saw in our previous example. Also worth noting, you need to use square root of minus 1 is I, and I squared is equal to minus 1. Also, so the real part, x we call a real part of z, and y we call imaginary part of z. So x is equal to, so that's equal to x, and that's equal to y. The complex number can be shown in a Cartesian form, and that's this form here. So that's called the Cartesian form. It's a Cartesian form of the complex number. So we can show a complex number on a diagram. So because it's a Cartesian form, a Cartesian diagram looks like, remember we had x and y. The only thing we make different, we say this is a real part of z, and y is imaginary part of z. So if you have a number, complex number z, you can show it as having the coordinates here of x and coordinates of y. But you can also say that x is a vector. So we can use vectors to work with complex numbers. So in that vector, you can say that that vector has the length of, so a vector has the length if it goes from the origin, and an angle. So this angle here is theta. So in a vector form, you can show it as like r is square root of a squared plus b squared. That's the length of the vector. And we say now, what if someone says, what's the square root of? So the simplest, say, complex number will be, say, 0 here and 50i here. That's a complex number too. So someone says, one question would be square roots of a complex number. So what it means that a plus bi times a plus bi, and that's the square root, so equals a plus bi square. Equals 50i. How are we gonna get the square roots of 50i? They're two square roots. So what we're gonna do? We're gonna break this down. So a squared plus 2abi plus, and you have bi squared times b squared. So because a square is minus 1, you have a squared plus 2abi minus b squared. And that's equal to 50i. First question, if we group this like terms, so that's grouping the like terms plus what's with I is 2ab equals 50. Let's write this 50 as 0 plus 50i, because for the real part we have 0. So we say now complex numbers are equal, so two complex numbers are equal, say a plus bi equals c plus di, only if a equal and only if only a equals c and b equals d. That's when they're equal. That's our equality of complex numbers. So here we have a squared plus b squared equals 0, and the second one says that 50i is equal to, I we don't need to write, because on both sides we can remove it, because on both sides divided by I. Yeah? So what you got? You got 2ab. So from here you have the a squared equals a minus, sorry, a squared, goodness, a squared minus b squared equals 0, so a squared equals b squared, and from here you have ab equals 25. So it's worth to highlight that what we are doing is doing square roots of a complex number. So let's make some room and continue. We'll make more room here. So that's about the equality of complex numbers. So only if the real part equals real and the imaginary is imaginary. So from here we have that a is equal. So from the first one we have that a is equal plus minus square root of b, square root of b squared, which is b. So a is equals plus minus b. And say, and we have the second one, ab equals 25. So case 1, we have a equals b, so a equals b. Therefore, b squared equals 25, therefore b equals square root of 25. And b equals 5 plus minus 5. So it's plus minus square root, so it's 5. If therefore we have a equals 5 and b equals 5, or a equals minus 5 and b equals minus 5. That's our case 1. Case 2, we have that a is equal to minus b, therefore we have minus b times b, so minus b times b equals 25, therefore b squared equals minus 25, which is impossible. Therefore you can't find two numbers that case 2 like that is not valid. So that's impossible for a real a and b. So here we need to know this is a real number, element of real, and this is a real number. So they belong to real numbers. Real number, and this is a real number. So these are element of real. We can denote that as x, y, element of real numbers. I can write that nice. Here x comma y, element of real numbers. So let's continue, make some room and finalize, write down our solution in the proper form. So we'll do that under where we started. So our solutions are a equals 5b equals 5. So from here we have 5 plus 5i, or now the other one is minus 5, so it's minus a minus b minus 5i. These are the square roots. Square roots of our of 50i. That's our complex number. Square roots of 50i. You notice this x and y are in real numbers. Let's continue with the operations with C, complex numbers. So we can add complex numbers or subtract complex numbers by adding or subtracting real parts and imaginary parts. Say a plus bi plus c plus di equals a plus c plus b plus di. Subtracting is similar. Taking is the same way. Imaginary parts and real parts together. So we have geometrically, we can do that geometrically. So if we do draw a diagram, so we said a number, say z, our z is x plus ey. Let's put our z somewhere here. So note a complex number is 1 point. That's our z. That's a complex number. So it's got into vector and its length. So now if we say we have another complex number, say complex number here, say called u, then we can add them like we do vectors. So to the end of the first one, so if you go z plus w, that means parallel to vector u is the same vector u. That's the same vector u. So you know, with vectors we can translate them to be parallel. They don't change. They're the same one. Therefore, if you join this line here, this vector here is u plus z. That's like with vectors. This is x and this is y. So see vector z, x and y components. So that's geometrically. So how do you subtract them to addition? How do you subtract them? Are the same as you do with vectors. So again, vector z, or complex number z, vector u. So how do you get a complex number? By if you join from, so you want z minus u. Yes, you have z minus u. So that's the same parallelogram. So if you were to add u here and there, that's the same. That was plus, and this is minus. You have this parallelogram. Please note that you start from the end of the second vector. So not like when you're adding to the end of the first vector, you're adding the second vector. Here, from the end of the second vector, which is minus u, you add a line to the end of the first vector. That's subtraction. Remember this, end of the second, end of u. U is important. So the vector starts from u, and here the vector starts from 0 and goes to, when those are string, you add it to the end of z. They're like adding, continuing to flow. And this here is subtraction geometrically. So addition and subtraction of complex numbers. So now multiplication. Of complex numbers. For the multiplication, we use two things. We use the distributive law, so a times b plus c equals ab plus ac. And if you remember, if you multiply a plus bi times a plus bi, it becomes a plus bi squared. So this is the huge binomial distribution. So 1, 2, 2, 1, 1, 3, 6, 3, 1, and so on. So it's binomial expansion. Expansion. So that's for the multiplication. And for division, you use, so we need to introduce one more term before we start with the division. So if you say a plus bi is a complex number, its conjugate is a minus bi. So if z is said like that, that z with a cap, that's a conjugate. So it's a new term, and what we know from before, we know if we multiply a plus bi with a minus bi, that's first square minus the second one on square, because the second one on square becomes I square. I square is minus 1, so that becomes plus b square. So this is called z. Absolute value of z. It's like square root of that. So we have that z square is a square plus b square. Yep. So basically what you got, this is your z, as said here, and times your z conjugate, and this is your solution. So what it comes to is z times z conjugate equals the conjugate is the absolute or is modulus of z on square. So it's the length of the vector z on square, modulus. So what we did is multiplication, we did the division, we can continue with the division, so it's just we continued here talking more about multiplication and new concept of a conjugate. So that becomes its absolute value, I mean conjugate times the complex number gives us modulus of z square. It's important to know. We'll continue with the division here. Continue the scheme. So with our division, say for example, what do we do with dividing, say a plus bi? We want to divide by c plus di. What do? We multiply the denominator with a conjugate. So in order to get rationalize, so we rationalize the complex number for division. So what we have, then we multiply c plus di multiplied by c minus di, and up there we have I plus bi multiplied by c minus di. That's how we divide a ration. And so what that becomes there whatever becomes, but down we rationalize it and becomes obviously c square minus d plus d square. So that is how we divide the numbers, the complex numbers c square plus d square rationalized. That's for division. So it's important to notice rationalize for division. Let's now continue with complex numbers, and we'll do something called the Moivre's theorem and polar form of complex numbers. So we'll start with the polar form. Let's make some room. So we're doing polar form of a very complex number. Polar form. The polar form. So let's see what that means. It's that form, the polar form we're talking about is the form in which the complex number z is represented as r cosine of theta plus I sine of theta plus I sine of theta as the form, the polar form. So geometry that is represented as, if we have x and y here and z here, so the length to z, you remember we had z modulo z is equal to r. That's our r. And this is our x coordinate. And here is the y coordinate. And the angle here is our angle theta. That angle there. So that's a polar form. So that's it. So it's not a vector, it's just a vector would have an arrow. But this is that. Imagine notice it starts from 0 and it's in that direction. It's not the opposite direction. It's nothing there. Just in that direction there. Notice that direction. It's nothing there, nothing there. And why is nothing there? Why is nothing here? Because we have this angle theta. It's from theta starts from here, goes here. So theta doesn't go all the way there. Say for theta, it goes only up in the first quadrant. No there for theta. So we also denote it as r cis theta. It's another way of writing it. So let's do an example. So what you can see here, you can see that x is cosine, it's r times cosine of theta. I'll show it in a minute. So r times cosine of theta and y is r times sine of theta. So what's cosine? Cosine is, so let's analyze this. What's cosine? Cosine is x divided by r. So you have r times x divided by r. So obviously it's x. Similarly here. So to remember, x is cosine of r, y is sine of cosine of theta, and r is sine of theta. Now, how do we get theta? Theta is x if you divide by x. So if you divide, say, y divided by x, what's that? Y here divided by x is tangents. So it's a tangents of theta equals y divided by x. So the other way of, but very useful would be that tangents is written as sine of theta by cosine of theta. Remember that there. So from there you have that theta is obtained from there. So therefore, to solve this equation, you apply arctangents on both sides. So if you apply in this equation, you apply arctangents on both sides, what you're gonna get? You're gonna get your theta. So that's your equation here. You get theta from here. And how you're gonna get that? If you try, so you get theta equals arctangents, or tangents of minus 1. That's the same as tangents in the power of minus 1. So of y divided by x. That's how you get theta. That's your theta. That's how we derive theta. Let's make some room. Let's z be 4 minus 4i. Let's find its polar form. X is then equals to 4. Y is equals to minus 4. Therefore, our r is square root of 16 plus 16 square root of 32, which is square root of 16 times 2, which is 4 square root of 2. So our r is that. Let's find out theta. The tangents of theta equals minus 4 divided by 4, which is minus 1. So we need to notice that y is negative, because the y is negative. This is our y. This is minus y, so y is negative. So it has and x is positive, therefore quadrant 4. It's here, somewhere here. And because sine equals to cosine, so that's the same as sine of theta by cosine of theta equals minus 1. And that's in the case that is when the case in theta is, so we need to go to get that. So we got theta equals tangent -1 of -1, which is in the fourth quadrant when sine and cosine are equal, that is pi quarter. So it's equals minus pi quarter. So that's our solution. Our R is that, and our theta is minus pi quarter. Therefore, our number looks like 4 square root of 2 times cosine of minus pi quarter plus I sinus of minus pi quarter. That's our Z. That's the polar form. We put theta to be such that theta is between pi and minus pi. So between pi and minus pi. And then we call it that theta is the principal argument. So it's the principal argument. So we focus on theta to be like that. Principal argument. Therefore we choose pi -1 pi quarter. Let us continue with complex number in polar form. Form part 2. Quick recap, that's the numbers of, if you write the numbers, complex number Z, and in its polar form is R times, and you have cosine of theta plus I sine of theta. That's the polar form. So if you have the number that is in the Cartesian form, then you know that to convert them you have x equals r times cosine of theta, because that the real parts and imaginary parts equaled, and y equals r times sine of theta. So that's the correspondence between the two. And tangents of theta equals y divided by x. You know what they look like. So if you have a complex number z, then its coordinate here is x, and the coordinate here is y, and this is your theta angle measured from x-axis. So your tangents, you know what we did then. You understand that now. So first we'll do multiplication in polar form. Part 2 will cover multiplication and division, as well as the Moivre's theorem. And division. So now if this is a polar number 1, so if that is z1, theta 1, and there is another number z2, say it's r1, we've got r2 times cosine of theta 2 plus I sine of theta 2, then your product z1 times z2 is equal to r1 times r2, and you sum the angles. Cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Your division is similar. You divide the modulo and you subtract the angles. Cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. That's very simple. What does that look like? So if here we draw first z1 complex number, and this is theta 1, and your second complex number, we'll make it a bit smaller, second, that's your z2, the angle here is theta 2, and then your product would have the angle first plus the second, which will come like something here. So this angle here is theta 1 plus theta 2, and the modulo, the length of this nu, so we call it z3. This z3, its length would be, and if we were to subtract from z3 by angle, it would be like going back to z1. z3 minus z2 will be going back to z1. It's all obvious from this picture here. So the modulus, the length of z3 is, say z2 is 1.5 and z is 2, that will be 3.5, approximately the length. So there is one more theorem. It says 1 divided by z equals 1 divided by r times cosine of minus theta plus I sine of minus theta. We'll call them theorem 1, theorem 2, and we'll call the S theorem 3. So that's what we'll use. And there is one more theorem called the Moir's theorem. Moir's theorem. And it says that if z is a number like z is r times cosine of theta plus I sine of theta, then it says that z on the power of n is the same as r on the power of n times cosine of n times theta plus I sine of n times theta. And that's for any n that belongs to the set of z. So n is an integer, positive or negative. So any integer, so it could be on minus n or minus theta. So the Moir's theorem can be used to solve the equations of the type like z on n equals and then any complex number. So you can see that it can be a equals 0 and I equals I3, like that, to be bi or similar. So let's try to solve a simple case where a equals 1 and b equals 0. So that's z on power 4 equals 1. Let's write both sides in the polar form. So we get 4 theta equals 0 plus 2kp. So for k and z we get solutions of 0, pi half, minus pi half and pi. So the solutions are and that's important, equally spaced. So that's very important. So that's applicable to everyone. In complex solutions are equally spaced. The solutions are equally spaced. And let's write down our second one. Thing that we said, just not to forget. Is the fundamental fundamental theorem of algebra says that there are exactly n solutions for a polynomial of degree n. So polynomial degree n has exactly n solutions on the complex over the complex plane. Complex numbers plane. So that we look exactly the fundamental theorem of algebra. And now let's record our solutions in the normal Cartesian form, not the polar form. So let's here make some room for that. So the first solution would be 0 per theta, so r is 1. That's our z1. Our z2 is when k is 1. So we have theta becomes pi half. Cosine of pi half is 0, but sine of pi half is 1. So we have 1 times I is I. Our z3 solution z3 becomes when k is minus 1, just minus pi half. Therefore cosine 0 sine is minus I. Sine is minus 1 times I minus I. And our last solution, z4, becomes when k is 2, it's pi. Cosine is minus 1, and r sine is 0. So our solutions are these are our solutions in Cartesian form for the equation of that z on the power 4 equals 1. We'll talk about the complex solutions. Or roots for polynomials with real coefficients. With real coefficients, so they always come in conjugate pairs. What it means that if z is a solution of an equation, then also z conjugate is a solution of a polynomial. Both are two solutions. are always present. Plus bx plus c, therefore can be written as a times x minus, say we call it alpha times x minus alpha conjugate. And now we have one more thing to consider, how to represent graphs in complex space. So graphs in complex plane. So we've done complex solutions. Sorry. That's what we covered. And now we'll cover graphs. So for example, let's draw a graph of z, absolute value of z equals 4. So how are we going to do that? We can do it algebraically or we can do it geometrically, depends what we... So we can do algebraically, or geometrically. So in this case, what do we know? We know that we have a number z, complex number, and we know that it is number 4. So can we somehow tell what if we want to represent it, say, in polar form, can we do it? We can't. So what we know that we can write that like this, expanded form, and it's 4. What's this modulus here? The modulus represents the distance. Don't we say that? That's our r. Remember, we said that our r is a square root of x squared plus y squared. It's the distance. Remember when we draw our complex number in polar form, then our r, if that's our z, that's our r. So r is there. This is the distance from the origin. So what we say that r is equal to modulus of z. So we know that our distance for this r is 4. So that's how we can say that the distance is 4. And we don't know, we can't tell the angle, because x and y, tangent is what? So it's only we know the distance. So if you don't know the distance, if you do know the distance, but you don't know the other two coordinates, you might think of that's everything on that distance. And everything on that distance is a circle. So that's one way of reasoning. Because x and y are unknown, x is not known and y is not known. Therefore, every x and y is okay. So that's one way of reasoning. It's geometrically thinking. But algebraically, we can say that we can proceed from here and say that what we wrote here we have that is equal to z absolute value, which is there, is equal to 4. So what we're getting that x squared plus y squared equals to 16, which is 4 squared. And this is an equation of a circle where the radius is 4. So it can two ways to the solution what this equation here represents. Geometrically or algebraically we come to the same. It's a circle with a radius of 4. X and y. So the solution is every x and y and radius is 4. Every x and y in a circle. Because the radius is 4. So let's try another example. How do you if you're given argument of say z minus 4 equals say pi third, what do you know? You do know the arguments, so but you don't know x and y. But you can say that argument of x minus 4 plus iy is equal to pi third. So what it tells you that the complex number will be in where x and y are in the pi third, so it will be an angle of 60 degrees, so it will be like that, angle of 60 degrees pi third. But where will it start? Will obviously be moved. It won't start, you don't know x and y, so every x and y that is on the pi third angle will suffice this equation, but you know that x is moved to 4 in the positive direction of x, if you remember drawing functions. So that's 4 here. So our solution will be AZ will be on this line. It's anyone on this line. Any set of coordinates is our Z. So that's our Z. Any set. So that's that line. The last in preparation is useful formulas. So we have modulus. So if you know that Z times Z complement equals modulus of Z square, if you remember those. It's number 1. Number 2, Z on the power 2 modulus is the same as Z modulus on the power 2. Number 3, Z times Z1 times Z2, and then modulus of that is equals Z1 modulus times Z2 modulus. Number 4, Z1 divided by Z2 modulus equals Z1 modulus divided by Z2 modulus. So some formulas about arguments. So argument, remember them. Argument of Z1 times Z2 equals argument to Z1 then plus argument of Z2. Remember that from the previous work. And the division the same. Argument of Z1 divided by Z2 equals of argument of Z1 minus argument of Z2. And the last one, the conjugate. Remember the last one in relation to conjugate is Z1 plus Z2 conjugate is the same as Z1 conjugate plus Z2 conjugate. And also one more, the 8th one, we'll put it there, Z1 conjugate, Z1 times Z2 conjugate, or equals the product of conjugates. So that's all our useful formulas.